All right, so in this video lesson, we are studying about double integrals. And so the topic in double integrals is always the first topic that begins our study in general about multiple integrals. Okay, and so let's find out what it is. All right, but before we begin right here, one of my permanent advice is that bring as much experience of your experience and understandings about your integral work from calculus 2 into this as much as possible. Okay. All right. So to really begin our study about double integrals, let's spend some time to understand and study about what it is to be a double Riemann sum. Okay. So let's start out with learning about a double Riemann sum. And so my plan for the lesson here, I am going to fire up a problem, okay? And we're going to learn through that function and through the given problem, we're going to study how we can come up with a double Riemann sum, okay? And then at the end, we're going to be able to formulate what generally a double Riemann sum is. Okay, so in this lesson right here, let me introduce the following function. Let's say we are starting with a given function f of x comma y equals 2 minus x squared minus y squared. And so this function right here currently being is a function of two variables. And that is the reason why we're studying about doing a double Riemann sum. So double means two. So double Riemann sum at this point now, anyone already had an expectation in mind. It's double, meaning two, so it's applied and only applicable to functions of two variables. Okay, the best place to study for that is for a function of two variables. And then later on, as we extend the idea into a double integral, so double integral is specifically meant for a function of two variables. Okay, we are integrating on functions of two variables. All right, but then in the end, let's get back to this particular function right here. So this this function of two variables right here. For now, let me start out with a given this function, and we're on a given rectangular region. Now, so note what I'm saying. Note my words right here. We're working specifically on a rectangular region. So now we're having that function over. So the region, I'm going to call it R. So rectangular region. Okay, so underline that word right here as a rectangular region. And let's name the region here R, and the region here, many textbooks writing it as following. 0, 1 with a big time sign right here. This is a sort of like a big crazy multiplication sign. Cross with 0, 1. So what exactly is this? Another way of seeing this is the integral. This is the regions where it's a combination of all x and y point on the x and y plane right here, where x is anywhere from, it's a closed interval. So this first part in the notation here is an interval, it's a closed interval on the x-axis. So in set builder notation, this is anywhere from 0 to 1. So this region is the collection, is the set of all points x comma y, satisfying that x is anywhere from 0 to 1, and then y value is also the same, anywhere from 0 to 1. And that's how we understand about this region. So many textbooks use this short way of describing what we have here as a rectangular region. Okay, and I didn't even get into what a Riemann sum, what a double Riemann sum yet. Right now I'm describing, hey, we have a function, two variables, f of x comma y equals 2 minus x squared minus y squared. And then we only going to restrict this function over a rectangular region. We're going to only study this function over a rectangular region. And that rectangular region, I name it capital R. And then this is how we write it more commonly. But then what to understand about that? It's the region, it's a set of all x comma y, right? Satisfying that x anywhere from 0 to 1. And then the same with y anywhere from 0 to 1. Okay? And so So to have a picture of the region right here, see, for this region, on the x and y floor, x-axis is here, y-axis is here. Okay, then just think about the interval from 0 to 1 on the x-axis. So you see the region was written as 0, 1. So the first part right here is on the x-axis, and then cross with 0, 1 again. So you can think of an interval time an interval, but it's not that time in the usual sense right here. And then there's an interval from 0 to 1. Okay, so the whole region is this nice rectangular shape. I mean, the picture itself is indeed a square, but in the end, it's got 4 corners right here. So we call it, it's more generally, it's a rectangular region. Okay. It's a rectangular region. All right, and so that's the region right there. So from now on, from this point on, anytime that you're seeing a convention as a region being named as some interval a comma b, from a to b, time with in product with this is really a Cartesian product actually, in case anyone do plan to go to a higher math right there, then a product like this is called a Cartesian product of an interval by an interval. And then from c to d, okay, so that means with a region like this, it is clearly as a convention, it's a rectangular region where the picture is, so on the x-axis, this first one here is the x-axis, is on the x-axis. Okay, and this next one right here is on the y-axis. That's the generality of how we understand. So on the x and y floor, C to D, some C to D on the vertical scale, okay, and then from A, okay, from A to B, okay. See, I'm trying to draw that as general as possible. So really, the rectangular region is like this. Okay, anywhere from C to D on the vertical scale, and from A to B. So this is the rectangular region I'm talking about, from A to B. All right, so that's how we are commonly indicating a rectangular region. So in our problem right here, the rectangular region specifically here is a square, from 0 to 1 on the x-axis and from 0 to 1 on the y-axis. All right, and I didn't even get to the double Riemann sums yet. All right, so now after clearing out my minor understanding that I wrote on the board here, let's focus on this specific picture right here. So the idea of the double Riemann sum. Now, let's say on this right here, along the x interval between from 0 to 1, so that's why, as I said earlier, take as much experience that you have done, that you have learned back from calculus 2, the integral calculus. Bring as much of those as in here as possible. So we're going to break this interval on the x-axis into a few sub-intervals. So let's say for here at start, I'm going to break that into 4 sub-intervals. But so now in a region, it's going to become like this. Okay, so I'm going to break it down into 4 sub-intervals. Okay, so that's on the x-axis, and I'm going to do the same. Now, in the real reality out there, there's no strict requirement that the number of sub-intervals on the x-axis and the number of sub-intervals on the y-axis have to be the same. Nope, there's no such a hard rule about that. And you can go 4 here and you can go 8. But my plan is, the idea is that we're going to have to break each interval here into a number of sub-intervals. So here on the y-axis, I'm doing the same, and it's just now to keep life simple for us. We're gonna divide it out evenly. So also 4 sub-intervals on the y-interval. So that's the picture. And so here I'm using equal number of sub-intervals on each way right there. That's just a choice, and we are allowed to do that. But as a generality, it's not a requirement that we go equal number of sub-intervals. All right. And so now all of a sudden we realize if we break 4 here and 4 on the y-axis, 4 on the x-axis, then we're having 1, 2, 3, 4, and then 4 more is up right here. 4 times up right there, and that means we got a total of 16 sub-intervals. 16 sub-partitions. Each one of the picture here is a sub-square, is a sub-region. So now to be precise, we call it as a sub-partition. Okay, so in this picture right here, so the better way of writing that is, see, this is row 1. Okay, first row. And indeed, I can, because the picture is standing up right there, but I should have gone with the columns right here. So the column right here is the first column, right? And then this one here, second column, and then third column. So these are in respect to the x right here. So each one of these, okay, each one of these got a, so my drawing is going to be a little too busy now, but each one of these is a delta x. See, each one of these little squares here got a space delta x horizontally. Okay, and each one of the, if we pick a square over here, right, or a subpartition, okay, if we pick a subpartition right here, then we have that vertical space in each of the subpartition. Each of the subpartition right here is a delta y. Okay, but then, so now my picture is getting busy, so I'm gonna really have to erase a lot of these. So just keep in mind, I use 4 subintervals here on each end right here, on each side right here, but that's generally, we can break it into some n subintervals and some m subintervals on the vertical axis right here. And so, now we're gonna need to organize. So I called that earlier, and now I just erased. Let's rewrite it. This one right here is, see, first column, right? First x column, and then this is the second x column. And so to make it easy, we're always going to use the x in the first index. And then now this one right here is the first delta y, and then this next one right here is the second delta y, and so on and so on. So first delta x, the second delta x, so on and so on. Each of these is, and at start, really in reality out there, again, since there's no hard rule about equal number of subpartition on each end, and as well as further, each one of the width right here, each one of the width in your picture right here doesn't have to even be equal. They can be, you know, a little bit big here and small there, and big here and small there. In other words, the width on each of these subpartitions does not have to be uniform width. All right. But now, if I pick a rectangle, so right now we're just trying to understand what it is. If I pick any rectangle, any subpartition, rectangle or square, it's just a rectangular shape. If I pick that one, that particular rectangle right there, then the width delta x, okay, is at some ith delta x, and then the y, the vertical space right here, okay, I can call this width. So the other one, I guess I call it length, okay. So the length here is the delta y, but at some jth subinterval on the y-axis, and that's why it's multiplying these two, we have what's so-called a dA, okay, a dA, and indeed the precise term, a delta A ij. All right. So the delta R and the delta A. So I use A for an intention. Think of that as a picture. It's an area. It's an area, right? A little area of that rectangle, of that rectangular shape, of that rectangular subpartition right at the ith column and the j row right there. All right. And so, but as an in-depth look, it is how much space on the x-axis and how much space on the y-axis multiplied together. And so that's what delta A ij is, right? That's the delta x at the ith subintervals on the x-axis multiplied with delta y on the jth subinterval on the y-axis. All right. And then each one of these points, now I'm going to use a red ink. In each one of these, actually, I set these points, but I meant in each one of these sub-partitions. We can pick a point right here. We can pick a point. And so it's such a, even though the picture is small, but it's such a, we can have infinitely many points in there. So we can pick a point here. The point can be inside of the square of the rectangular shape, or it can be right on the boundary as well, or it can be on anywhere of the corner. So the point can be inside or on the edges or on the corner, any one of the 4 corners in each picture. But then a point like that, I'm going to call that, yes, I'm going to make another red arrow to point down here. With that point right there, we call that it's a sample point. Okay? It's a sample point. It's a sample point. And then that sample point right there, many textbooks call that, any point on the x and y plane now it's a pair of values x, comma y. And I hope anyone viewing the video lesson here agrees with me. X, comma y. Being a sample point, it's a point that we choose. So I and many textbook authors use a star here to indicate it's a point that we choose that belongs to one interval, one subpartition. Okay, and then this is on the ith x subpartition and on the jth the y subpartition. So it's a sample point. That point right there in red. All right, and so now that's the idea right now. It's a sample point. So any subpartition at a specific location, at a specific position on the ith column and j row right here got a sample point in that we can pick. And this sample point right here we can pick. Okay? And so now, again, my picture is already getting quite busy. I'm going to erase out some of these writings right here. All right, so after reconstructing a different picture over here, then let's say we're going to right at that, let's say I'm just going to focus the picture right here, right at that corner picture, and it could be the same for any other picture over here. Right at that picture, I'm going to pick a sample point. So how about I'm going to redraw this in a 3D version. So in a 3D version, this rectangular region is going to look as following. That's the x-axis. That's the y-axis. Okay. And indeed, allow me to change my mind a little bit, because now when I put that in a 3D version, I just realized that if I drew a picture from this rectangle, it's going to make it harder for me. So I'll go with this. Let's focus to this one, on that particular rectangle right there. So now on the 3D version of the same picture, I'm going to try my best to create that nice square rectangular regions on the x and y floor. 4 sub-intervals on each way. So that's the picture. So that subpartition is right here. That subpartition. And so now think about and right in there, as I explained earlier, there are so many sample points that we can pick in one subpartition. So again, choosing a sample point, there's no generality, there's no hard rule about that. As a matter of fact, they don't have to be the same sample point. But it is allowed to go with the same sample point, the corresponding sample point in each of the partitions here. And so for this picture right here, let's set out with a rule. Let's set out with a rule that I'm going to choose the sample point being. So let's go with that sample point at the bottom corner right here. Okay, that's my sample point. So out of the whole square that we focus here, out of that whole square, let's just pick that point. So that means on my picture, it is going to be this point. That's our sample point. Okay, so I'm going to just pick, so that at some I and j, okay, position, at some I and j position. That's our sample point. That sample point is chosen here, and on this version of the picture, it's right there. All right, but now what can we do with that sample point? The idea now is that, and start bringing up your imagination. If we're substituting that sample point into the function, so this is one sample point we have already chosen for that particular rectangle, and we have our right to use the corresponding sample point. So if we're looking at the next rectangle here, then it's going to be that sample point. And if the next one is down here and the next one is right at the origin, and so on and so on. So on this one right here, it's going to be that corner, for example. Okay, so we can set up for ourselves a rule to make life simpler for us right here. But now at this step I'm about to do, on each sample point, on each one sample point of your, or in each of your sub-partitions, right? From the sample point chosen, we're going to substitute that into the function. And so as a picture, substituting this into our function, we have a height. I mean, the output of the function is being represented as a height. And so now I also have to erase or reposition my writing right here. The sample point, okay, is right here. But now from the sample point, if we're substituting that into the function, we got some height. The idea is this height is how much the function output is given. So the height here is determined by the function's output. Substituted that pair of sample point in there, that pair of values for the sample point in there. Okay, and then, so right at this rectangle, I chose that sample point, substitute, and then I substituted that into the function. I obtained a value, and then the value is being visualized. Is being visualized as a height. And don't get me wrong, it doesn't always have to be positive. So the function itself that we're starting here is an f of x comma y equals 2 minus x squared minus y squared. So I'm experienced enough that I can see that this function at least is above the x and y floor in this region, in this rectangular region. That's why I drew the height going up. In other case, if the function happens to fall negative, okay, in this region, then the height is going to be the negative height, sinking below the x and y floor. But the point now is that once we have had a height, right, that's how we picture it, then we're going to multiply that with the delta A that I explained earlier, and I had to erase that. It's at the same location, ij, at the same location. So everything we're doing is on one specific subpartition. So doing this right here, here's the picture. See, whatever that height is, right? The picture is going to give us a rectangular prism. Okay? A rectangular prism. But now, what about that rectangular prism? Really, this work right here, this calculation, substituting the sample point into the function to get a height, and here we can think of this as an area. This is an area, it's a small area of that subpartition, and then this is the height right here. This is just how we visualize it. Okay? Then multiplying height and area, hey, what do we get out of that? We get the volume of this prism. So this is one prism right rising up right on top of that subpartition, ij, that ij subpartition. Okay, and so now think about it. This is one small volume, and we can call this a delta V, or whatever that is. You can name that whatever, but it's a delta V. It's just a dummy variable, but it's right at that ij subpartition. We got some kind of quantity. All right. So now for the rest, I'm going to do, and at this point it's way beyond my drawing capability right here, but on each one of these squares we're going to rise up similar prisms on each of these other subpartitions. Okay, and so this is where I need to turn over to the computer station right here and have that graphical illustration. Otherwise I cannot really proceed with the permanent drawing like this, because I'm not skilled enough. All right. So here's my graph, and I hope the picture is showing clearly enough, and it's in 3D perspective, so we may realize that it doesn't look like a square right there, but it is meant to be a square. And then you can see that this is that subpartition I was talking about, and then this point is where I was talking about on the x-axis. And so now, as I said earlier, we're going to build all of those prisms. So now let me rotate the picture, and you're going to immediately see what I'm talking about. And this is on the same function, 2 minus x squared minus y squared. All right. Right there is our picture. So that first prism is indeed right here. Right? So it's right here, it's rising right there, and whatever the height, it's determined by that corner point right there. Okay, and then the rest of the other prisms are all here, and I hope anyone viewing this lesson can see the boundaries of each of these prisms. All right, and so back on the board right there, and maybe it's better that I leave the graph still on the blended together with the picture here. So if we would now, so the idea is we're gonna, as I said, I'm gonna make all of those other prisms rising up from those sub-partitions evaluated at those points right there. All right, and so that means now after having a whole bunch of prisms like that, each one of those has a volume. And so now what do we do with that? So right from that picture right here, after having so many prisms rising up from the number of sub-partitions, and by the way, we got 4 on each waves right here, on each of the waves right here. So we got 4 times 4, that makes a total of 16 sub-partitions. And so after rising all of those, as you're seeing on the picture, after rising up all of those right there, I'm summing up all of those prisms volumes, all of those prism volumes, and see, volume is, and again, don't get me wrong, but volume is just a way I'm using right now to represent, to visualize the picture right there. Okay, but the idea is on each of those sub-partitions, we got a product. So after rising up, so in some other problem, in some other function, the prism may go downward. Okay, and in some other problem, the prism may go the upward. And some function it may be even going up in a certain area, in a certain sub areas of the region, and then go negative. So prism may rise and may fall below the floor all over. But the idea is on each prism we do this calculation, this products between the height, it could be negative, okay, the height of the prism multiplied with the area on that sub-partition. So now I'm summing up all of those. So be careful, it's a 2-dimensional floor here. So summing up means we have to sum all of those, all of these this way and all of those that way. Okay, so that means now on this particular problem I'm doing, so on all of those, right? So let's start back from each of the specific one. Okay. For each function evaluated at each sample point in a subrectangle, and let's write it in the complete version. The delta A ij right here, we can think of that as a delta x I multiplied with a delta yj. That product right here, I'm summing all of them. But see, that's why now it's called a double sum, because the idea is just summing it all up. But when we're summing it, we're doing that with a certain procedure, orientation. So we're summing up all of those on the x-axis first, right? Along the x-axis. So that's why we're summing all of those on the x-axis. And that goes, index I is going from 1 to the end of those generally. Okay? Or for here in our particular problem, why not just stay focused right on our problem right here? Okay? That's 4. So we're summing up those prisms from 1 to 4 on the x-axis. All right, and then once we're doing that, we're gonna sum the other way. So now that's why now it's called a double sum. We're summing all of the j, and think about it. Once we're finished summing up all of those in one column, in one row like that, right? In one row like this. Once we have summed up all of those prisms, we got sort of like a wall, and then we're summing up the volumes of those walls out. And so that's from the j, starting from one index to the last one right here. Okay, so this, ladies and gentlemen, right here, it's called, this is a sum, and it's a double sum. And so at this point, I've had the picture on the graph here long enough. And allow me to erase this picture. All right, so this here is a sum, and it's a double sum. And then I did that quick calculation earlier. It's 4 by 4, 4 times 4. Or in other words, it's a sum of 16 sub-partitions in it. And some textbook authors skip this, and some other textbook authors keep it there. I belong to that group who keep it there to make it clear that how many we sum on each wave. All right, but ladies and gentlemen, this one right here, this sum right here is called the the double Riemann sum. All right. It is the Riemann sum that we've learned from the calculus 2 ideas here. Okay. We pick sample points and then we sum, and this time the reason we call it double because we got the two ways summing up. Two ways of summing up. So this right here is called a double Riemann sum. Okay. Of the function f of x, comma y over the region R. But then specifically of 60 sub-partitions. And 16 because it's 4 by 4. All right. And so now generally, okay, so generally speaking, as far as what it is to be a double Riemann sum, okay, then think about for a region, right, from A to B, a rectangular region, and then C to D right here. So this is our rectangular region, right? And we're breaking it down into some n number of subintervals on the x-axis. Okay, and then some m number of subintervals on the y-axis, just like that. And then we pick a sample point on each one of these. Then an n by m. So here there are n subintervals. Okay, and then here this way there are m subintervals. And yes, the region R here is A comma B by C comma D. So with a region like that, then the double Riemann sum, in a picture like that, the sum that's called S sub n by m, okay, n on the x-axis and m on the y-axis. Doing that, we can just go the function as x sub I comma y sub I, but with the star here, those are the sample points, right? We multiply with delta xi times delta yj. And that product, we're going to sum all of those on the x-axis, meaning index I from 1 to n. And we sum further on the y-axis, meaning index j equals 1 to m. The sum like that is the and so as far as the formal definition is the double Riemann sum. Right. And of course, save me from the worded so much wordy writing right here. So that's what the Riemann sum, the double Riemann sum is. And then further, we're going to be precisely called that of the function f of x comma y, right? Some whatever function that is. In our study, it was the function 2 minus x squared minus y squared, but here is generally for any two variable function. Okay, and then over the region R from A comma B by C comma D. Right, that region is the rectangular region. So that's how we define the double Riemann sum. And so the n by m right here does also intend that eventually we're gonna have the n times m sub terms right here. We're gonna have so if it's 4 by 4, then we're gonna have a total of 16 terms being added together. So that's what's so-called a double the Riemann sum. So in the end, I'm explaining and right from the picture of our particular problem. This definition came out from our function being for this. Let's take a quick note right here. The function was 2 minus x squared minus y squared. Okay, and then we call that the double Riemann sum, and in this particular function here, we in this activity we did that in 16 subpartitions, 4 on each way right there. What's useful about this? I mean, what's the application? Where's the usefulness of doing something like this? Okay, so as far as the usefulness, and right now it's just one among infinitely many usefulness out there. But as far as an application, okay, for firing up a double Riemann sum, here's the idea. Now let me bring back the picture. And right there we got 4 subintervals on each end right there. Okay, so the actual graph looks like that of the function 2 minus x squared minus y squared right there. Okay, and let me turn that away that a little bit. But then, so in the end, the purpose here is that, see, and I brought up the graph to emphasize that at least in this rectangular region that we focus our function to, that we narrow our function to, in this rectangular region, 0 to 1 on the x-axis by 0 to 1 on the y-axis, in that rectangular region, our function there is positive. Okay, the function you're seeing right there is positive. See, you see that dome is staying above the x-axis? I mean above the x and y floor right there. Okay, and so truthfully, as far as an application, I mean, what's good about coming up with a double Riemann sum? So one of the direct implications, one of the direct application is that if our function, right, and our function in this activity is apparently greater than or equal to 0, but in general, if the function is a function being greater than or equal to 0, okay, on that on any region, rectangular region, okay, on the region R being a rectangular region. If that's so, then we can think of this double Riemann sum as the approximates to the volume. Okay, the volume, and now when I'm saying the volume, I mean the volume between the volume that's created by the surface of the graph and the x and y floor and restricted in between this rectangular region. That volume now can be approximated by the Riemann sum, the double Riemann sum, by breaking into n subintervals on the x-axis and m subintervals on the y-axis. That's one of the applications, the volume. And so now the volume. So let me show that picture right there, right here in our problem. And you have already seen that earlier. See, the volume here, when x equals 1, it reaches to right here, and when y equals 1, it reaches here. But so it's this part of the volume. Okay, so that precise volume can be approximated by the sum of all of these inside the prism volumes right there. Okay, that's what it is. So the double Riemann sum, as long as our function is positive in that domain, and you saw that on the graph earlier, as long as that dome was above the x and y floor, and so now over that region, we knew that the dome was above the x and y floor on that region right there. Then the volume in between, right, can be approximated by this double Riemann sum. That's the usefulness of doing the double Riemann sum right there. All right. So, but then at this point, for anyone who are strictly calculating about volume, and think about eventually sooner or later we're going to face with a problem calculating volume. Is this the precise volume? The question is this the exact volume, the exact amount of volume? No, it's not. And so this is why I had that advice earlier, that bring as much experience and as much understanding from your calculus into this lesson as possible. Because the idea now is that we're not going to be happy with 4 by 4. It's not precise enough. We're not going to be happy with 10 by 10. So indeed, we want to keep increasing the number of subpartitions on each direction. And then there's no hard rule about they have to be equal, but we can always allow ourselves to go with equal subpartitions on each way right there. And so now back on the picture. Okay, and I cannot, in my picture right here, I cannot make it all happening at once. So I'm going to, on the x-axis, I'm going to break it down into 10, on one direction. I'm going to break it down into, how about 10 subpartitions. Okay, and you can see right there. So that's along the x-axis actually. Okay, so on the x-axis, I purposely broke it down into 10 sub-intervals. And you can see that we got better approximation. And now I'm doing the same on the y-axis. I'm breaking it down to also 10. Okay, and now the picture got a lot more refined. Okay, and so the volume keep getting better and better to approximate the actual volume. So the sum here keep getting, so to be precise here, the sum of all of these prism volumes right here keep becoming a better approximate and better approximate of our actual volume, our exact volume inside of that dome, restricted in this rectangular region from 0 to 1 and 0 to 1. Okay, and so in that way, and that was only one demonstration of the usefulness. Okay, that was only one demonstration of the usefulness. At least what it is to be a double Riemann sum, right? We have learned it, and that's just now what I finished writing down on this board here, and that's what a double Riemann sum is. Okay, but then, and I showed a picture that we keep increasing the number of subintervals, and we got better approximate of the volume. We'll get to that. All right, and so now we are ready to push into the next definition. And for anyone learning at this level, for anyone learning in this video lesson right here at your level, now I can skip over quite some number of details right there from your past understanding, but you can always bring it back in. So as far as the definition, okay, so the double integral, that's how we call it, okay? But what is it? You got a function of two variables, and as I said earlier, double integral is meant specifically for a function of two variables. So with a function of two variables, okay, a double integral in a setup as following. So anytime that you're seeing something like this, the function multiplied with some dA, okay, multiplied with some dA, and then the reason we call it double integral is because, see, there's integral sign, but it's a double integral sign. For now, just keep it on that simple side right there. Let's stay with the simplicity, with the simplicity that hey, double integral just means we see two integral signs right there over a region R. That symbol is indicating what we have here as a double integral, and I'm about to write down what it means by having this double integral. So that symbol there is called a double integral. Okay, so this double integral here is defined to be, and that's why it was important that I gave that definition of what a double Riemann sum is. And so now think of the double Riemann sum again. We first of all start out in the region here. I'll even explain better about that region later. It's a rectangular region, okay? But similar to what I've been going through in a rectangular region, I'm going to break it down into multiple subpartitions, and then on each sub-rectangle at an ij position, I'm going to substitute a sample point into the function to get some kind of height, right? Positive height or negative height, and multiply with the delta xi, and multiply that with the delta yi. Okay, so this here, I'm going to produce the double Riemann sum. Right. From n to m, I from 1, j from 1. So the double Riemann sum, the double integral, is indeed not only a double Riemann sum, but it's the double Riemann sum where we allowed. So let me write this in right here. we take a limit as we allowed n to infinity and also m to infinity. It's a double, so it's starting out that we are doing a double Riemann sum at some finite number of subpartitions on each way, x and y axis. So we got a whole bunch of terms to add up, and then we're going to increase the number of subpartition on each way right there. That's why there's this limits notation. That we increase n to infinity and m to infinity. That's why I brought in that understanding earlier that, hey, what if I was not happy with the approximate of the volume? Then I'm going to increase the number of subrectangles on the region right there to 10 on each way right there. So 10 by 10 is giving a better picture. See, right now on the graph, right now it's at 10 by 10. I increase from 4 to 10 on each way. And then I can go 20 on each way, 20 by 20. We get even better approximation. And of course, it's computers, so as we keep increasing it, it takes more computing resources, so it takes a little while to load the picture. But right now we got the 20 by 20. So the point now is that to reach to what a double integral is. It is starting out being a double Riemann sum, and then we infinitely increasing the number of subpartition on each way right there. And that's how we get to what's so-called a double Riemann sum. And so now this is where you're going to start bringing back your past understanding in terms of an integral right here. What's happening? Think of the consequence as we keep increasing the number of subpartitions. Then each amount dx, delta x, delta y here doesn't matter if it's I or j, but each of these keep getting smaller because in the end we're fixed in a certain window. The certain window is the rectangular region. So once we're in that fixed rectangular region, okay, the rectangular region, once we are set out for that, right, it's a fixed rectangular region. And then in there, if we keep breaking into more subintervals and more subintervals, then what's going to happen? Each one of our width and length right here of the rectangle is going to get smaller and smaller. And eventually when it gets infinitely many enough so that each of these becomes so small, they become just simply a dx times a dy. And later on we're going to see something like this. So dA, really think about that as a dx and dy. These are the differentials in x and differential in y right here. And then when it gets so small, your sample point doesn't matter if it's in the middle or in any of the corners right here. It becomes simply just the function at that instance, x comma y. And then that's where we're having this double integral over the region R. The region R right there. So that's what a double integral really truly is. It started out, we defined that as a double Riemann sum, and we're taking n to infinity and m to infinity. Yeah. And with this definition right here, allow me to write in a couple explanations. That so R right here, okay. So to complete this definition, where R is some region, some rectangle. So what we're learning right now is, needless to say, it's double integral that's specifically for a rectangular region. Okay. A comma B by C comma D. All right, and of course A on this is on the, allow me to go informal a little bit, the X interval. Okay, and this is the Y interval, not intercept, interval. Okay, the interval on the x-axis and the interval on the y-axis, respectively. Okay, and so that's how we define the double integral. A double integral over a rectangular region. This is a rectangular region. All right. That's how it happens. Okay, and so as I said earlier, I pointed out in the graph right there, I increased from 4 at start with a double Riemann sum, and I increased to 10 on each way. And I got a better approximate of the volume. And then I got into 20 by 20, and you saw that on the picture. Right now, currently, I'm at 20 by 20. Okay, and I got better approximate. Keep getting better, closer and closer to the actual. And so Again, don't get me wrong that this will always give you the volume, but at least what is a good usefulness, a good application of calculating a double integral, of coming up with a double integral. What is it for? Okay, so again, now allow me to bring up another brief application. So, if our function is specifically non-negative on the rectangular region R being a comma b by c comma d, if the function is non-negative or above the x and y floor on that rectangular region, okay, then I was talking earlier about the volume. Then the volume, okay, so let me bring up that illustration in our particular problem that I'm doing here. I'm talking about, so now, and I'm not the best artist here, but it kind of go like this, right? All right, so there's a surface of the function, and then that's the amount of space, right, trapped between the surface and the x and y floor, and restricted from between 0 to 1 and 0 to 1. That's the area of that's the rectangular region that we're talking about. So as long as the function is above the x and y floor, right, then the volume, now I'm talking about the exact volume. I'm not doing this wiggling lines anymore. The exact volume of that picture, okay, can be obtained by calculating the double integral over the region R for that whatever that function is in respect to dA. All right, that's one usefulness of that. Okay, and so that's how it is. And then in the next problem right there, in the next topic that we're heading into, we're gonna exactly learn, because at this point we just learn what it is, but we didn't really get too far into the how we can calculate it, because right now all I'm seeing it's a summation of infinitely many prisms volume right there. But then in the end, at this point, after you have seen the pictures, we got infinitely so many prism volumes, and then we're accumulating it. Now it's the right time that I'm saying this again. I keep saying this to my calculus 2 students, and anytime they're starting into, anytime that they've learned about long enough into integrals, and now I'm repeating this to anyone learning multivariable calculus with me. An integral is accumulation. An integral is accumulation. So right here, a double integral is a double accumulation. We're accumulating in the x direction, in the y direction, to come up with, well, in some applications, to come up with volume. In some other applications, we come up with other things like that. All right, but an integral, including a double integral that we just learned, okay, over rectangular region or whatsoever later on we're going to learn, is accumulation of the prism volumes like that. Okay, and don't get me wrong, prisms here, it's just because it's positive, so we got volume right there. In some other times, the prisms falls below the x and y floor, right? And so, as a remark here, let's take this here as a remark. After that, after I have explained one of the applications, then as a remark, a double integral, and at this point we still have not learned how to calculate one yet specifically. We didn't learn any methods yet, but after knowing what it is, a double integral over a rectangular region is not always a volume. Okay? Yes, I pointed out, but see, I used that term earlier. It was just one among the applications. So in some time when we met the requirements, when we have a satisfying requirements that the function is a surface above the x and y floor, then yes, doing a double integral can reach us the volume between the surface, the floor, and inside of the region. But it's not always, that's just one among the applications out there. It's not always going to give us volume. So it's good that we think of that as volume, but again, to be clear, a double integral over a rectangular region is not always a volume. Okay? But now, at this point right here, just right here, with what we have seen, it's enough to mention one property here among many other properties, and we will study the other properties as we go along. But now, for this point right here, I can proudly present to you one of the important property that's easy to catch right here. When you are taking the double integral over some rectangular region, and where your function is a constant c, okay, on that, when your function is a constant c on that rectangular region, this is a double integral. Your f of x comma y is a constant. That's why I'm writing it like this. That right there is exactly the same as, now many textbooks write it as the following. Write it as the c value multiplied with the area of the region R. Many textbooks write it this way. So A in parentheses R means the area, and I'm talking about the actual physical area, the area of the region R. So it's c times with the area of R. But in this lecture right here, allow me to explain that a little further. So I'm going to provide my own interpretation. Well, in the end, right now in our learning, right, and the R here is, we restricted our understanding to the R being a rectangular region. Yes, R is an A comma B by C comma D, and so that R right here, that area is the same as B minus A, the length on one dimension, multiply in products with D minus C, the length in the other dimension, times with the constant C. So this part right here is the area. That's how I'm seeing it, the area of the rectangular region R, and we multiply with C. Okay, so that's one property. Okay, that's one property. And so here's the thing. We didn't learn how to formally calculate a double integral yet. We only understand what it is as an explanation in terms of the Riemann sum, a double Riemann sum. But believe me, with our limited understanding up to this point, we can still come up with an informal. I'm only saying it's an informal proof. So I'm going to try to give an explanation. But it's not a formal proof yet, okay? Because in the end, we're learning math. So you just don't want to take whatever the instructor up here is telling you, okay? We got to have a sense about how it can be true. So to prove that informally, think about this picture right here, okay? Yes, as far as an application, right? Then as long as the function is positive right there, then the volume can be obtained by that double integral. So now on the other hand, right now we still did not cover all the cases yet, but to prove this particular property, and we will come back and reinvestigate this later, but I'm just narrowing that into one case right here, just for now, assuming that the function is a constant being positive constant, or how about non-negative? See, so assuming so in the region A comma B by C comma D. So in that rectangular region, let's just assume this, and then later on when you've learned more experience, we're going to come up with formal proof where it also covers other cases where C is below 0 or C is equals exactly 0. For now, non-negative. And mostly I'm focusing on positive. But that just means we have a flat surface somewhere, okay, a flat surface somewhere above the region. Okay, and so that height is always C. That's the height right there. And so in your region, it's going to be like this. All right. And that's the reason why it's just B minus A is right here, this length right here. That's B minus A. And this length right here, that's d minus c. Length times width times the height being c. Right there. That gives us the volume. So in that, when we narrow it down particularly to that case right there, we already see how truthful it is, because see the volume, right? The volume of this picture is c, the height, right? Positive height times with b minus a times c, I mean d minus c. Okay. But this volume, according to what I just erased earlier, and you've seen it on the board, that volume here is also the same as the double integral over the region R of the function c, okay, dA. That's how it's true with this property. All right. X-axis, y-axis, this is the z-axis. That's how we can informally prove this first property, and there are other properties that we will investigate as we go along. All right, and so at this point, we are close to learning a method for specifically calculating a double integral. We definitely don't want to go through the double Riemann sums. Now, back in the old days when students were learning calculus 4, they were asked to spend a day or so, right, to really crank through the double Riemann sum process and then increase the number of subpartitions to infinity, like that, to get a double integral. And the video lesson here is designed not for that purpose. And so if the video lesson here is being incorporated with some other in-person learning portion right there, then I will be able to show some of those kind of problems in person during the in-person portion right here. But for the video lecture, I'll just get straight to the point. I'm going to show directly a method how we can calculate the double integral without going through the Riemann sum, the double Riemann sum. But now, before we getting into the double Riemann, before we getting into the actual methods, now let me introduce another terminology right here. And this is very important, and I need anyone learning from the lesson here to pay close attention, because I myself, back in my time when I first learning it, it took me a few years misunderstanding. It took me a few years misunderstanding about this right here. So now I'm introducing for you what's so-called an iterated. Okay. An iterated integral. It's not quite right at first. It's not the same as a double integral. Okay, an iterated integral. So what is it? You got a function f of x comma y right here. Okay, and so now let's write it as specifically dx dy. So an iterated integral is written like this. The double integral sign is all like that. Two integral sign and then just commonly a region. So, and I mentioned it earlier, an iterated integral is not, right now I didn't intend that to be a double integral. So right now all I'm seeing, we're going to take an integral from a to b. And notice, for the first integral sign right here, from a to b, I go with the x-axis. Okay? And then outside of that, I'm going to go another integral sign. See? And that's levels right here, and accumulating from c to d. This is what I call an iterated integral. But how do we calculate it? How do we calculate an iterated integral like this? So, yes, so this is how I define that. Okay? A picture like this, a setting up like this, a writing like this, a notation like this. And this is, again, it's not the same, right? It's not the same as the one double integral sign right there over R. It's not the same as that. Okay, keep that in mind. And the reason I so emphasize that, because I myself fell into that mistake for some few years back in my learning right there. So this is called an iterated integral. The way to calculate this iterated integral, indeed it is actually a definition. We define an integral in this way to be, first, on our function f of x comma y, we are calculating an integral that's so-called, sort of like, I see that as an inner integral, or on one-way integral. I'm going to integrate that in respect to x. Okay? That's why it goes along with the integral from a to b. So now it brings back calculus 2 understanding. And then once we're done with that one right here, we're going to integrate this outcome in terms of in terms of y. And we're integrating that from c to d. That's how we define an iterated integral. So with this iterated integral, you can see that the order of the integration matters. We're doing from a to b on the x-axis first. And then once we're done with that, see, that's why it's written down right here. And then once we're done with that, right, and then we're going to integrate this outcome right here on the y-axis, but in between, from c to d. And so upon defining this iterated integral, there's another iterated integral. And I'm not saying any connection between the two here. Be careful, I'm just giving two separate definitions. This is definition number one, this is the definition number two. I'm going to define a different iterated integral. This time on the same function, f of x comma y. But I'm going to write my notation as a dy dx this time. And then the first level is from c to d. And this is only working right now on rectangular region. Okay? And then the outer one is from a to b. So it's a separate iterated integral compared with that. I'm not saying anything about these or being equal or not. Okay? The way of doing this is defined to be, yes, according to the order, you can see that right there, the function f of x comma y, we're going to integrate in respect to y first, right? From c to d. And then from there, we're going to integrate again in respect to x from a to b. And that's how we define two iterated integrals. There are always two of them. So keep in mind again, they have right now, I don't need you to think of any connection with the double integrals we've learned. These are just different things I'm calling them. I'm not calling them double integrals. I'm calling them the two iterated integrals. Okay, we're doing integrals step by step in one direction, and then the other direction. That's why they are defined being done like that. Okay. All right. But so now, upon taking that definition of iterated integral, then we have the following theorem. That's called the Fubini's, and I hope I got that pronunciation correctly. This is called the Fubini's theorem. All right, and so I'm sure whichever textbook that you're doing, but I'm sure your textbook, they gotta mention this theorem, and they may call that theorem 6.1. Some other textbooks, they put that in chapter 10, they call that theorem 10.2, whatever, but mainly it's called the Fubini's theorem. Okay, credits to that mathematician Fubini. But anyway, Fubini stated that, hey, the double integral over a rectangular region. So this is, I'm talking about a double integral over a rectangular region. There's a connection, and Fubini proved it, have proven it. That can be done by doing the iterated integral from a to b dx dy, and then with the outer one from c to d. That's one way. So you can now do this double integral by firing up the iterated integral in that order. A to b first on respect to x, and c to d on respect to y after. That's one way. Fubini have proven it. Okay? Or that same double integral can be obtained by doing the other iterated integral from c to d, integrating from c to d on this function in respect to y first, and then in respect to x from a to b. That's what Fubini's theorem is stating here for us. That's how important it is. And so now you don't have to do both. One of these two is your choice right there. Okay? But what does that mean as a consequence? As a consequence, as a further consequence, any one of these choices get us this result. Okay? So this is the way to calculate a double integral. But now as a further consequence, we realize, oh, wait a minute, so the iterated integral from a to b on the function okay, with dx and then dy from c to d. That iterated integral is indeed equal to the other iterated integral from c to d dy dx from a to b. So all of a sudden, now earlier when I was stating the definition, earlier when I was giving this definition, I keep telling you to keep these as two separate definitions, and I didn't need anyone to see or to recognize a relationship between these. But now after studying Fubini's theorem, then now all of a sudden we also understand as a consequence these two iterated integrals are always equal in final value. All right, and so we're using these as just simply a choice to get to the final value of the double integral indicated here. All right, and so of course the proof I'm about to give here is not a formal proof again, because it's a video lesson. You don't want to spend a lengthy amount of time to watch me proving every single step. But think about the iterated integral. It serves that purpose, and specifically this setup right here. This setup, any one of these two setups, is claimed to be the answer to our double integral. Okay, so why is that? Let's ignore the outside part. Think about this case right here of our iterated integral. The inner integral here on respect to x, right? It's accumulation. Right now, it's an integral accumulating on the x-axis. But think about right now, how is it connected to being a double integral? If we're only accumulating on the x-axis, right on the graph, right here with the picture, hopefully it's good enough. Now I'm going to have to really zoom it in a little bit. Okay, but if we stay at one. Think about if we stay at one particular y value, and accumulating that, so we're gonna end up with a slice. All right. So if we fix the y value and accumulating only on the x-axis, we got the thin volume of one slice, and that's one slice right there that I'm pointing it out. That one slice right there is the result coming out from integrating this. And so we got the volume of one slice. Then once you got the volume of one slice, you want to further accumulating those slice volumes from on the y-axis. That's why there's the integral of dy coming in. And so now again on the graph right here, see, once we have arrived at the volume for one thin slice, right? Now we're going to integrate all of those slices, right? Volume from the beginning to the end on the y in respect to the y-axis right here along the y-axis. So we start at 0 for y and we're ending at 1 for y. We see we got all of these thin slices right there, right? And so that's how we got to the total volume. And getting volume is one perfect example to a lot of time explain, the double integral over a rectangular region. And so that's how the Fubini stated that doing the double integral, one way you can do it like that. You're accumulating on the x-axis first, and then we're accumulating on the y-axis. So what about the other ones? So, well, let's have a look at the order of operation here again. Here in this picture, I'm accumulating just that inside right here, in respect to y first. So now think about on the graph, I'm going to turn it this way a little bit. I'm going to freeze my x value at one particular instant. I'm going to freeze my x value at some instant. And so I'm going to accumulate all of these prisms volume all on that same x value, but then for y changing from 0 to 1. So accumulating that, I'm going to get the volume of one thin slice. And that's what it means by integrating in respect to y first. And then now, but like I said, when I was integrating in respect to y first, that means we froze our problem on one slice of x. But now once you have done getting the area or a general formulation of the area at any instance of x, now we're going to accumulate further in respect to x. So each of the x now is going to be a slice Okay, on each of the x here is going to be a slice volume. So we got so many thin slices with volume, and we're accumulating that further out from 0 to 1 on the x-axis. And that's how we're getting the total volume. And that is, in this case right here, as an application, the double integral. And so that's why Fubini's theorem has proven for us that to get that double integral right here, the way to do it, instead of doing infinitely or hopelessly the double integral and letting the number of m and n to go to infinity, we can just do either one of the two iterated integrals here, and we're done. All right, so that exciting time is here. We have finally found, I brought up this function way at the beginning of our lesson here, but I didn't get anywhere too far into that in terms of just aside from just beating around the bush, explaining the double integrals and then what it is to be a double integrals. I mean a double Riemann sum and then a double integrals, but we didn't get too far. So now let's get to it as an example, as our formal example here. And we're going to really see the core understanding of that. I'm going to let f of x comma y equals 2 minus x squared minus y squared. Okay, with that function, two variables, we want to evaluate. Okay, we want to evaluate the double integral over a rectangular region R for our function f of x comma y, okay, over that region R. And then of course R here is that region from 0 to 1 on the x-axis by 0 to 1 on the y-axis. So this is the exact repeat of the problem I introduced, but we never got an answer to that. So now we're going to learn the exact method to find the exact answer. So according to Fubini's work, well, the double integral over the region R is on this function, 2 minus x squared minus y squared, right, dA. So that's the double integral. But then Fubini's theorem said that we can, as a choice. So it just means that I'm more comfortable with starting out with the dx first. So I'm going to do this. I'm going to produce one integral from an iterated integral with a to b on the x-axis first. So now it's 2 minus x squared minus y squared dx dy, and then c to d. So this is an iterated integral, integrating in respect to x first, and then integrating in respect to y after. That's how we're doing it. And so now the formal work. And by the way, I should have used 0 to 1 and 0 and the other 0 to 1. Zero to 1, 0 to 1. All right. And so now with this work right here, yes, I'm going to do 2 minus x squared minus y squared, integrating that in respect to x first. Okay. From 0 to 1. And then whatever outcome of that, I'm going to integrate that in respect to y from 0 to 1. I'm just rewriting the iterated integral. Okay. All right, so now at our current step right here, this first inner integral, we're going to have easily come out with, see, 2, integrating that constant in respect to x, we got 2x minus, it's an x squared term, so our understanding of the fundamental theorem of calculus comes back here. 1/3 x cubed minus, so now it's a y term right here. Got no x, so think of that as a constant, right? So in integrating in respect to x, we got y squared x right there, and we're evaluating that from 0 to 1. And whatever that outcome is, we're gonna integrate further in respect to y. All right, so now I'm gonna evaluate this according to the fundamental theorem of calculus from 0 to 1. So I'm gonna produce the following. So the inside part right here before the dy is going to give me, so 2 minus a 1/3, okay, minus a y squared. And anyone learning in this lesson is experienced enough, so allow me to skip a few elementary steps. We're integrating again from 0 to 1. dy. And by the way, 2 minus 1/3, we can combine like terms, right? And making it 5/3 minus y squared. And so now we have a function completely in terms of y, and now we're integrating that in respect to y. Everything is ready for us. So that now becomes 5/3 y minus a 1/3 y cubed. And now we're evaluating this from 0 to 1. And that now gives us the final double integral value. 5/3 times 1 minus 1/3 times 1 cubed. All right, and that is simply just altogether 4/4. That's our final answer. So that's the double integral. All right, and since this is one formal example, allow me to roll back to this point and emphasize that Fubini's theorem says this was just a choice. So I could have also done since the region here is quite square from 0 to 1, 0 to 1, so it won't make much difference. But the other iterated integral I could have used right from the beginning. So when you're doing your work, you don't have to do both. Just one is good enough. You can go dy dx. And that means you're going to integrate from 0 to 1 of 2 minus x squared minus y squared in respect to y first. Whatever that outcome will be, you're going to integrate again from 0 to 1 on the x-axis, along the x-axis. That's how it is. And so, at our current step right here, proceeding into it, this inside integral right here gives me 2y minus x squared y minus 1/3 y cubed. And then I'm going to evaluate that in respect to y from 0 to 1. And then whatever that outcomes will be, I'm going to integrate again from 0 to 1 in respect to x. And so using the fundamental theorem of calculus, substituting 1 here for every y value and substituting 0 for every y value, we're producing the following integral. 0 to 1. The integrand here becomes, so that's a 2, because 2 times 1 minus x squared minus a 1/3 times a 1 cubed right there, so 2 minus 1/3, right? And then we're integrating that again in respect to x. And then, yes, 2 minus 1/3 can be combined even further. So I'm going to rewrite this. It's just I'm short of board space, so I'm doing this informal work right there, but 2 minus 1/3 is a 5/3. So it's a 5/3 minus x squared, and we're integrating that in respect to x. And so that now becomes a 5/3 x minus a 1/3 x squared. All right, and then we're evaluating this from 0 to 1. And so that means now we're going to do a 5/3 times 1 minus a 1/3 times a, and by the way, there should have been a cube there. So times 1 cubed. All right, and so now that gives me a 5/3 minus a 1/3. That's making it all together a 4/4 again. And it should equal with the earlier results that we've done. All right, and so this example here emphasizes and enforces, okay, our understanding of the Fubini's theorem. And that was, and that is, will always be the way of how we calculate it, how we calculate a double integral over a rectangular region.